now in front of a live studio audience.
And live studio. That means you all have to laugh at my jokes. All right, hi everyone. Welcome to week 5. I hope you all are surviving so far at college, especially you freshmen who are new. I would like to say it gets better. It doesn't. It's worse. You just get more and more homework. So this week, our agenda. So first things first, we're going to talk about outreach. I just confirmed this with Dawn. If anyone doesn't know, Dawn is over here. She's one of our outreach coordinators. We're going to be meeting at the Pit this Monday from 1 to 1:30, talking to a group from Society of Women Engineers, SWE, and just kind of show them the Pit, show them the robots, show them how we build and design. If anyone is free and wants to hang out, see our robots, maybe see them drive, you are more than welcome to. I'll be there. It's a great experience just to be able to teach kids and see their eyes light up and actually get them interested in engineering, especially since women are an underrepresented field. It's good to get them in engineering early. So I highly recommend if you can be there. It's a good outreach event. Speaking of outreach, I've mentioned before that you meet some really cool people at NASA's RMC, both the judges and the engineers and all that, but also the other teams. This past year, we helped out a team, the University of Portland. We printed a bunch of stuff for them. Their motors kept breaking, and so we were able to use our 3D printers and help them out. And they reached out to us this year, and they contacted us saying, hey, we would love to have this kind of collaboration throughout the year. The idea being we're not worried about them stealing our ideas, but we all want to go to NASA. We all want NASA to do as well as they can, to share the best ideas, come up with the best robot, and we're going to be able to do that by cooperating. If we have an awesome team of engineers here, they have one in Washington, so let's see what we can do to help each other out. The president of the University of Portland, their club, he's from Utah, so it's probable that he'll be here at some point, either fall semester, spring semester, so I'll bring him by. You guys can meet him. The admin team is going to be working with both the University of Portland and the University of Washington, just so doing occasional chats, updates on where we are, ideas we have, ideas they have, collaboration on the rules, what we think. And along those lines, if any of you guys are on Reddit, Cole is actually the moderator of our NASA RMC.
Of the dead one.
Of the dead one.
There's 2 RMC subreddits. There's RMC NASA, the NASA RMC. Whichever one is more active is the one to be on that I'm not a moderator of. But there's a lot of good discussion that goes on in there. Teams are actually kind of active. I know that Alabama has a person on there.
Kentucky does.
Kentucky, and then a couple other teams.
So they're a good resource to talk on Reddit or on Facebook. They have a bunch of groups on there. But throughout the year, we're going to be working with these 2 colleges, maybe Akron and Case Western as well. So we're going to be talking with them and seeing what's going on. How many of you are interested in the 3D printing class on Friday? Got about 10.
Does everyone know what we're talking about?
Anyone got any questions about 3D printing? All right, so this Friday, we're trying to kind of have a cool event every Friday or every other Friday. I was I guess I still am, the 3D printing guy in the team for the past couple of years. And I taught myself 3D printing from thermoplastics to rubber, and I'm teaching myself ceramics right now. And I figure the more of you that know 3D printing when I leave, the better the team will be. So we're going to start doing these 3D printing classes where I teach you the basics of how to design a model, what the parts of the printer are, what plastics you use for what situations, how the printer actually works, when to use 3D printing, when not to, casting versus molds versus 3D printing, that type of thing. The first class will be this Friday at the library, Marriott Library in the Knowledge Commons area. You are all welcome. It will be pretty informal. It's a 2-hour session. I'll bring my printer. You guys can check it out, maybe do a print or 2, maybe work with TJ and see if we can go in and back and see the big printers. What's up?
Did you say what time?
5 to 7 p.m. So that's this Friday. And I will say, I'm going to ask that you RSVP, and I'll tell you how in just a second. RSVPing on Slack. How many of you are on Slack? Don, what's up?
Is it okay if you're able to arrive a little bit later, like at 5:30, just because of
Yeah, that's fine.
work?
Let me see the hands for Slack again. Sorry. Is anyone not on Slack? All right, cool. If you're not on Slack, find Cole or me after we break up, because this is going to be our primary means of communication from now on. There may be the occasional mass email blast, but those are a pain. I have to limit how many I send at a time, like 20 of you. We have our main email list, so Slack is a much easier, better way of communication. So if you keep an eye on the 3D printing channel, if you join Slack and join that channel and say I will be there or I won't be there, I can plan for how many people we have.
How
So-
about we do emoji vote?
Emoji vote, yeah, that works. I'll do it. If you can make it on Friday, just emoji on the comment, and I'll know who's going to be there. Again, that's this Friday from 5 to 7.
Yeah.
Is this a one-time class or is it recurring?
So it'll be recurring. It won't be every month. Every month we're going to try something different, but we'll be doing 3D printing again throughout the semester. Let's see. Slack is one thing we mentioned. Another project another kind of tool we're going to be using this year is Open Project. It's a systems management tool and project management. It's more complicated and less kind of team messengery. This is more for TED and understanding where we are in our project, our goals, our deadlines, if we're meeting them, if we need to cut a goal, so on and so forth. If you go to usr.coe.utah.edu, Cole, will you write that on the board?
It's on the.
Oh, it's on the slide? I put it on the slide.
So go there under login. You can click that and click select create an account. We will authorize all of your accounts so you can kind of see what tasks we have to do by May to get a cool robot going to Florida.
And
If you ever
also, we're going to use it, we're going to use it for individual task management, so your team leads can assign you to stuff and give you deadlines, and we can follow up with you using Open Project.
Cool. So those are our two main processes of Open Project and Slack. So if you aren't on either one of those, you're probably going to be lost pretty quickly because those are our two main means of communication. Like I said, if you're not on Slack, talk to me or Cole sometime during the meeting. We'll get you on there. The last thing really is this is going to be a little bit of a longer meeting tonight because we've got to solidify what we're building from the various subsystems. We've got to choose inside that. And we're also going to have Ted talk about the overall systems engineering process. So right now we just ended phase A, and he can explain more of what that means and what we're going to be doing moving forward.
Right now? Okay.
Right now. This is Ted being glorious without a beard.
Yeah, that's me without a beard. If you're curious, when you go to NASA, if you want to be the person that loads the robot in the arena, you can't have a beard. So, because you got to put a face mask on. So, in a nutshell, we are in phase A right now. We're going to try and end phase A tonight. And we're going to move into phase B. That's our preliminary design phase. I'll have more details about that later. But essentially, the goals for phase B are going to make a prototype for our mobility chassis and a digger. And we decided to extend phase B a bit and shorten phase C because we figured we could get some of the designing process out of the way and kind of give us a head start getting into the final design and fabrication. And then last but not least, oh yeah, so phase C, that's our final design and where we actually like build our final robot. And then by phase D, which is January, we want to have like a full scale, ready to go, working robot with all the autonomy and all the happy motor controllers and everything working on it so we can do testing in our pit. So that's that. Right now I'm going to go through something called the ConOps or concept of operations. And this is kind of just, I know you've all kind of gotten the spiel about how the competition works, that we're digging up dirt and stuff. This will hopefully give you a little bit more detail. So this is basically the model of the arena for this year. You can see the dividing line. Two teams will compete in this area simultaneously. So you'll have Team A here, Team B there. And they will each go for a 10-minute competition round. And that's going to start with some NASA engineers giving us a random location and random orientation for the starting position of our robot, which I'm representing with a little Curiosity rover. And then after we get our robot in the pit and they start the competition, our robot has to do some things. Pretty basically, it has to be able to localize its initial position. Recall that for sensors and autonomy, we cannot use the walls, we cannot use compass, and we cannot use GPS. So in order to know where the robot's going to go, we have to know where it's starting from so it can actually navigate. And then part 2, we have to drive to the mining area. And I was kind of looking through the rules. I couldn't find any specifics about how the arena will be divided in terms of starting area, obstacle area, and mining area. I'm assuming they'll release those details later, or I'm just stupid and I missed them. But I'll let you know that as soon as I know that. And so some requirements for part 2. The robot shall be able to navigate the mining area from a random location and orientation. And it shall drive to the mining area and back to the collector trough autonomously. And it shall navigate through terrain and obstacle rocks autonomously. And it shall be protected from the BP1 dust. Now, get out my laptop for a second. So there's some details about that I wanted to talk so that Mechanical can be aware of it real fast.
While Ted's doing that, one of the reasons why they don't have the rules up for the mining area is on the pit right now. It's a new pit that's made a little bit smaller from the previous years, and the actual dimensions aren't finalized. So when they are finalized, the odds are that's when we'll know the exact locations.
Okay, so you see the little designation here that says Rule 3H.I. So Rule 3H is like a whole bunch of stuff about dust. And so specifically it says the robot shall have custom dust sealing features. The robot shall have active dust control features, and the robot shall complete all aspects of the mining cycle without kicking up dust. Did you have a question, or are you just holding your pencil up?
I'm just holding my pencil.
Okay. So I'm not too worried about the active dust control features. I feel like that's the kind of thing we'll get to it if we can. But kind of an idea of it is last year we stuck motor covers on all of our drive motors so that as we were driving we didn't throw up dust into the bearings and stuff. Okay, so, and then part 3, we have to start digging some stuff. And for that, so NASA specifies that like the gravel, the good stuff, the stuff that's actually worth points, starts at 30 centimeters below the dust. So we gotta dig below that if we actually want to get any like mining points. And we have to dig 1 kilogram of that material to actually qualify for any points for the mining round. And so I've set a goal in here that we will dig at least 3 kilograms of the BP2 in our 10-minute competition round. And also, like I said earlier, we have to do it without kicking up any dust. In previous years, like people have had like really fast, aggressive belt diggers that just like throw like a giant cloud of toxic dust into the middle of the arena, and NASA doesn't like that. So next, we have to return collector. The requirements for that are pretty much the same as part 2, but backwards and with a little bit more weight. But we also have to keep in mind the location of the collector bin. And that leads us to part 5, where we deposit all the collected material and go back for more if we have time. So for that one, they've given us pretty specific dimensions of the collector bin. And so in our mechanical design, not only do we need to have a design for a good digger, but we also need a good place to deposit and contain all of that BP2 material and find a way to dump it. And so with that, I'll turn it over to Dave.
So now that Ted's done, we're going to be going into our various subsystem discussions. From here, the team leads are going to talk about what each individual team came up with last week. Usually our top 1 or top 2 picks, and then we're going to open it to the floor saying, we like this system, this is why, and then you guys can come up with objections, questions, that type of thing, so we can rationalize and say, sure, treads are better than augers, or wheels are the best thing ever. So we have our top 2 picks for most of the systems, and then at the end of each various subsystem, for example, once mobility is done, we'll know what system we're using for our robot. So right now, I'm kind of the de facto mobility lead. Last week we did our weighted matrix, and we came up with Tweels and the rocker bogey system being the two leading systems. I will note that we can, for all intents and purposes, we consider the rocker bogey as rocker bogey with solid wheels, not Tweels. So they were weighted differently. The Tweels came out ahead, but the rocker bogey wasn't that much behind. Does everyone know what a Tweel and a rocker bogey is?
I don't know what a rocker bogey is.
You don't know what a rocker bogey is. I have pictures. So our four options were auger, so auger screws. That's what this looks like right here. Fun fact, this is the University of Virginia. They always show up and do really well. The robots, you pretty much can't get it stuck. It's pretty cool. Auger screws. This is the very first robot. We call it Old Betsy. Treads, obviously. Tweels, and then a rocker bogey is this system right here, where you have the front two wheels connected on a hinge, and the back wheel is separate, and all three wheels can kind of move independently of each other. A real rocker bogey system, if you see these represent motors, so the wheels are actuated, so that kind of like your car, so they can turn individually of each other. Every Martian rover except for Sojourner has had a rocker bogey system. So it is what we use most often on Mars. It's essentially one of the best all-terrain systems you can build for terrain you don't know. So that was one of the really strong points of it. So, like I said, Tweels, this example right here, and the airless tire, that got the most points. At the very beginning, we had talked about kind of combining treads, Tweels, and rocker bogey, but that kind of got weeded out. It is possible that we could have Tweels on our rocker bogey, if we think that's a good idea. Does anyone have a preference one way or the other? Is anyone really in love with not using a rocker bogey or only really in love with Tweels? Any questions about either?
So just to clarify, when you say just Tweels, you're kind
Four
of
wheels.
talking like the sound crawler, fixed
Yes,
frame?
fixed skid steer Tweels.
Okay.
Do you guys know what skid steer is? I'm getting a shakes of yes. Does anyone not? Raise your hand if you don't know what skid steer is. So most of you know. So a skid steer is when each individual each wheel has its own motor, but it's fixed solidly to the frame, so it can't turn. So if we have to do a 0 point, if we have to turn, say, either turn both the right wheels and you don't move the left wheels, or you turn the left wheel one way and right wheel the other, it's called a 0 point turn. But the wheels are stuck in a certain orientation. So you're kind of skidding and steering one way or another. I'm trying to think of a good example other than like big mechanical front loaders. You don't really see very many of them because they don't have the best usage. There. Tanks. So yeah, usually you see them with treads. Treads are pretty much essentially a skid steer. Say again, Tina?
Lawnmowers.
Lawnmowers. That's another
Some
good example.
lawnmowers, I guess.
So like I said, Tweels and rocker bogey. I know, for example, Ted has been really wanting to look into rocker bogey. I think it would be a good kind of innovation, a new step forward. Tweels give us really good. One of the reasons why we've done Tweels before and why they work really well is because they're kind of a mix between treads and wheels. You get added traction, you have a built-in suspension system, and they're durable. Plus, we can 3D print our Tweels, and we have it set ready to go essentially right now. So it's something we already have and we've done before. And then if we threw them on a rocker bogey, we could kind of combine the best of both worlds. There.
I personally like skid steer wheels a lot, just because it's simple and easy to do. It doesn't require a whole lot of, re-engineering our mobility system.
Mm-hmm.
I'll second that.
I have a quick question.
What's up?
From the past year's experience with Tweels, have you had any problems with getting stuck on rocks or anything?
So we've done Tweels once. We didn't move a whole lot. That was probably a combination of both getting too much deflection from the Tweels, and we had an underpower system.
So what I'll add on to is skid steer has to be designed properly. I think this last year we had small tires and a long wheelbase, which didn't allow us to get good stability on uneven terrain. So I think with skid steer you kind of want short robots and large wheels, so you get a little bit easier to turn rather than trying to turn like a semi-truck without turning your actual wheels.
And one more thing I'd like to add to that is with the fixed wheels and with no suspension in there, if you get in a situation where you end up such that you only have two wheels
touching the ground, then you might not have enough torque to keep the robot moving, which is what we had this year.
I was thinking, just from looking at it, I think skid steering would cause your wheels to kind of dig into the ground more, but you
have that
couldn't lose
problem.
traction because you just bottom out.
Yeah, I can say that.
Well, and I think it's important to realize in a skid steer you don't always have to 0-point turn. You can provide, say, 50% power to your motors on your left side and 100% motor, 100% power to the motors on your right, and you're gonna do a left turn, but in, at a given radius. And so that reduces the skid, the scrub on your wheels, so it's easier on your turn.
So go ahead, go.
I was gonna say we have to remember that we're in a confined space, so that may not be possible. And then back to what you were saying, a lot of teams do dig themselves in doing 0-point turns. So that's a known problem that a lot of teams have.
It's skid steered, yeah.
Yeah.
Right, and I think that's why we should go with the wheels and the bogey with the twills, because I can see with the skid steering, I mean, potentially if one of your wheels or a couple of your wheels gets stuck, it becomes very hard to move. Whereas if you have 6 wheels or wheels moving independently, it's a lot easier to get yourself unstuck.
Tina,
So how does the rocker bogey turn? Is it like the front 2 wheels?
turn one way, the back
Turn
two wheels
right.
turn the other way.
Okay.
So, with complexity, that's what I'm concerned about with the rocker bogey system. Are we adding motors for the turning?
Yes.
Okay, so that's another 4 more motors, and 4 more motor controllers, and 4 more connections and wiring going there. Also 2 more wheels. So that's gonna add at least 5 kilos.
That's true.
That's a lot.
You in the back.
Quick question. You said the one on the top left is proven that works well for Virginia Tech, you said?
Yes.
With wheels, that sounds like it's kind of iffy with the rocker bogey thing. Doesn't sound like anybody's really tried that one before.
The rocker bogey, some schools, the University of Portland actually tried this past year.
Were they successful?
To an extent. They didn't mind enough to qualify, but they did drive around and they were able to drive around the course.
Okay. What about the difference in weight between the one on the top left and the rocker bogey with wheels?
So last week we did the kind of design matrix and we kind of compared one versus the other. The auger screw, we would have to, one of the reasons why we decided that wasn't one of our top 2 picks was the weight would be more and it's harder to manufacture.
Okay.
Right, so I just wanted to ask, with the rocker bogey, can the twills turn both ways, all of them?
Yes.
Okay.
Except for the middle ones.
Well, so the 4 corner wheels have independent turning. These 2 were just skid steer.
Right,
Two
but I meant like rotate both ways.
Yes.
Like,
So, like John was saying, there are pros and cons to each. Some general pros and cons. So, pros and cons of both the rocker bogey is the all-terrain, the traction, not getting stuck, the skid, actuated wheels. It is something we've never done before. It is a layer more complicated, especially with more motors, more wires, more motor controllers, and it will be heavy. That being said, if we get stuck, it's much harder to get stuck if we do this correctly. And this is more kind of what NASA has in mind for our rovers, and I think it'd be fun, most importantly. But my say is in the end all be all, we are a team. So I'm gonna try to wrap this up in about 2 or 3 minutes, but do we have more comments?
I think it'd be better to take a chance on more weight than take a chance on being stuck. Because if you're stuck, then you can't do anything after that. But if it's more weight, at least if you get stuck and you can get out of it, keep competing.
So I will say you might not be aware that NASA weights weight extremely high for the competition. It's about 8 points lost for every kilo. Not about, but it is exactly, right? Have they changed that?
I don't remember, but there is also the point that, I mean, if you can't dig anything, then those points are meaningless anyway.
Right. Just in previous years, we lost mining because we weighed 60 kilos instead of 50. And we mined more than 90% of the other teams, but we took like 5th because we weighed a lot more. Well, a lot being 10 kilos.
I think it's also one thing I would say is another benefit of the skid steer is that again it's easier to build, and so we have that plan to build a second chassis. And if it's a chassis that for the most part you've already done once before, it's a lot easier to make, and that provides us a lot more time to get it to work right, versus if we have a long lead time on a rocker bogie because we've never done it before, we could, get to when it was supposed to be done and be like, oh, we haven't finished.
Let's see where we're coming from. Where
So-
it gives us buffer.
How does mechanical feel about designing a rocker bogie system?
Mobility, if you're interested.
What was your analogy about a Prius? Your Prius
Sasha?
analogy, like,
Well, one of the biggest things is innovation for NASA, and I feel like combining tools with the rocker bogie would really set us apart.
That would be pretty much the max innovation that you could get for
Yeah,
this.
exactly.
Just kind of going along with that, I think it was Ted that said last time, like a big part of the competition is kind of innovating and challenging yourself, and I think it'd be a good learning experience to attempt something that's that hard or more hard than just the basic skid steer. Right, and I also would say, kind of with his point, like we haven't done it before, there's going to be some overhead associated with doing the rocker bogie, but there was at one point that overhead associated with the skid steering as well. And so maybe we don't implement that perfectly this year, but we'll have that framework set in place, for the next year and following years. And so then that will be there.
Alright. So I'm about to wrap this up. It looks generally, so how about this? We're going to be building the prototype chassis to begin with. Let's step forth going with the idea of being rocker bogie with wheels, and if it's too much, we move to skid steer, something we've done before. We can use the buffer that we know how to do. But if skid steer with wheels turns, so it's our backup. But as of now, mobility is rocker bogie with wheels. Everyone good?
All right.
Sounds fun.
Question in the back?
I have one question.
It'll be great, John.
Yeah.
I'm sorry that I'm late. The digging mechanism is how?
We haven't got there yet.
Okay.
Everyone, that's Aaron. He was one of the founding members, so if you haven't met him yet.
Bye, Aaron.
Hi. I believe the next one is digging.
All right. So we've come up with 4 different ideas. We have a hybrid ladder bucket and continuous digging system. This will be an extendable conveyor belt with a digging mechanism on the very front of it. We will plunge this into the ground. The digging mechanism will kick the dirt material back onto the conveyor belt, which will then relay it up to the collector bin. The next is the bucket ladder. We tried this last year, so we already have a decent design in place. We did not get very far with it because of some power issues and also the way that some motors were implemented. So we do have an idea of how to implement it, but the issues that we have with it are ready to be overcome as well. The drum digger here is a large drum with teeth on it that are spiraled inward. So it will go over the dirt in paths that will move the dirt into a smaller conveyor system that will push it into the collector bin on the robot. Then we have the front loader, which is the same design as Amy, which will go in and do scoops.
You see them everywhere.
Yes. As it's looking now, bucket ladder is the leader and drum digger is second.
I should point out the fact that we did this way a little bit differently than we did with mobility, because we had a really good discussion with the design matrix with mobility and that design system that we ran out of time. So with this one, Nathan sent out a poll to the people on the mechanical team saying, fill out watching these videos, what we know, these descriptions, and then we averaged out the scores and we got bucket ladder and drum digger for the 2 primary choices. So this was done a little bit differently, but that's how we ended up with the 2 that we got to choose from.
Yes.
Okay, so I just wanted to ask, how do you plan to separate the gravel from the dirt that we're going to be digging?
Probably mostly through the belts will be perforated, and the scoops will have holes in it as well. The ice that we're going to be mining is a certain diameter. So as long as we have holes just under that, we should have no issue separating out.
You also have to remember that NASA doesn't really care if we deliver any BP1. Like,
Yeah.
we can deliver it with the ice or without, and they don't give a preference.
Yeah.
Right,
So
that's
that is
Um,
true, but I would add on to that we have to dig through 30 centimeters of
Oh yeah,
dust
yeah,
first.
no,
so
it's going to be best if we can get rid of it.
but we don't want to
if
take
it's-
up space in our collection bin with stuff that's
Oh,
useless.
definitely not. No.
Yeah.
Just to clarify as well,
Space.
I do have pictures as well. So the middle picture here is the belt ladder that we have. It is explained here as well. This is the drum digger idea. It is used primarily in milling machines to remove the top layer of asphalt to lay more down. That's where when you're driving and your car goes but into a kind of a hole in the road. That's from that. This is the front loader idea, as well as Amy in the side. The big monster of a machine in the corner there, next to Dave, is what's called the continuous miner, and more specifically, we'll be using the bottom half. This is what will be at the end of a conveyor belt, scooping in the dirt and bringing it up to the robots collector bin.
Like Nathan said, our two primary choices were the drum digger and the belt ladder, like what the Sandcrawler has here. Pros and cons of each. Pros of the belt ladder is we've done it once before, this will be our second iteration, and in general, the more you do it, the better you get at it. Most teams go with some type of belt ladder or some type of bucket ladder. It's a very popular design. It's effective, it can get deep quickly, which is why we chose it last year. Some cons are, you can see there that there's a lot of buckets. There's a lot of potential fail points, the chains might fail. We had a very innovative way of getting deep, but that's going to be something we have to tackle this year, is getting the bucket ladder deep enough to the 30 centimeters. So there's a lot of moving parts and things that can go wrong, but if you do it well, you can get it a lot right away. For the drum, it's simpler in a way. It's pretty much one component. The cons of that are it's heavier, it's going to require a lot more torque, and like Nathan said, it's easy to dig yourself into a hole. Some teams that have used it, I don't think North Dakota did. There are a couple teams that have used a bucket digger, not a bucket, excuse me, a drum, that I've seen. And they usually they don't do badly, but they're not, if you can tell by the fact that they don't remember them, that they don't do extraordinary either. So those are the two that would be, so the bucket, the drum would be much heavier probably. We need bigger motors, bigger torque. We need to plan our pathways differently. The bucket ladder, we know, but it can fail in a spectacular amount of ways. There's change or belts which can be difficult to use. So there are pros and cons of each. Does anyone have any general questions about either? Cole.
So it seems like the drum digger is good at getting hard material on the surface. How effective is it digging down to 30 centimeters and then getting the hard material?
That will be the hard part. It would require multiple paths over the same area, but then we have the issue of how big the hole gets, and then getting out of the hole itself.
How do you
Then
collect the
pick up?
material?
Yeah, like how do you actually get the material with the spiky drum?
The teeth are in a helix pattern, as you can see. So like this is a convergence point, and so it will spin in a certain direction, and it also acts as a channel. So as it breaks it up, the channel will circle it in to the center, and then at that point, this convergence point kicks it up into a conveyor belt to take up to the collection bin. Yes, right.
Just a comment on, and I'm not sure if I'm misunderstanding this. On the continuous miner, when it's going down,
Yes.
it's not going straight down because you can't get that up with a conveyor belt. You're having to come in at least a 45-degree angle at minimum.
Yeah, it would be at an angle. Yes.
Meanwhile, you can pretty much go nearly straight down with a belt miner.
Now, since we don't want to collect the BP1, would we be trying to get the BP1, take it up, and drop it off somewhere else? It's not back in our hole.
We would have.
Because we want to like have buckets be slotted and have just kind of dropping the same stuff back into our same hole. We might want to get it out.
Yes.
And then get it elsewhere.
Yeah, that'd be one of the designs that we'd have to look into. So we had the perforated buckets here, and also that's how we use the transducer to vibrate the plate that was underneath that was perforated as well to remove it, to remove the BP1.
The idea behind this was kind of like having an active sieve, so that we dig and sieve at the same time. So the dust stays where it is, but the gravel comes with you.
Yep.
He's got kind of a point though. I mean, it didn't occur to me with last year's design, but it might put more stress on our digging mechanism if we're just letting the dust like perpetually fall back into the hole. But
I mean, I guess one thing you could do with that, so instead of sieving from the buckets, you dump the dirt into the bin where the regolith's going to be, and then you have the sieve at the bottom of that lets the BP1 back out. And so then it would sort of collect, maybe you could dump it out the back of the robot somewhere.
so we kind of did that too last year. We had like the collection belt, but the collection belt was perforated, so that dust would fall through it.
Yep.
It is an option though. It's good.
Yes.
Tina.
Would we be doing the collection belt, like you have it all on the belt and then the belt just goes and digs, or are you gonna actually have like a little container that holds the BP, everything, the regolith, everything?
We could do either. Probably
Yes.
what we've done before, like you know, is we did the belt, but
Mhm.
that's gonna be something we test. That would also kind of be dependent on the chassis. What we want to
Okay.
do. If we can incorporate the belt, that would probably be better. But that way, we wouldn't have to we wouldn't need like actuators or anything like that.
Yes.
With the bucket ladder, will it have to be kind of take like stretches back and forth digging down, or to be able to dig?
In general, they're stationary straight down.
Yep.
Aaron.
Since automation is important, how many teams have automated each different kind of which type of digging mechanism has successfully been automated before?
The only automation that's so
Only the
case-
bucket
ladder.
Only
yeah.
the bucket ladder, is that right?
Yeah.
I believe so.
Yeah.
I'm trying to think of what North Carolina did. I think they had a bucket ladder.
But I think that's just mostly because like automation's hard. A lot of teams like don't get time for automation. Kind of like we do.
Bucket ladder is the easiest to automate.
It's the
as well.
easiest
Okay.
to automate.
Definitely the easiest to automate.
So it's sounding, just from the general questions we're getting, that people are going along the lines of bucket ladder.
Yeah.
Getting
Is that
right?
correct?
Everyone cool with the bucket ladder? All right, cool. Sounds like we got a rocker bogey, which wheels, and a bucket ladder.
So, I will ask with the rocker bogey, everything has to be contained within, well, I guess it's the same with our last year's design too, but everything has to be contained within the width of the wheelbase.
Yes.
Yeah.
And the rocker bogey system is going to add more width to the actual wheel mechanisms, so we'd have less digging area on anything that we use, unless we were to use something in front of ourselves. So,
I would say width for digging mechanism wouldn't be the worst downside. We had a fairly wide
We had
bucket
a
ladder.
huge belt last
Yeah, we had like 6 inches wide of a bucket ladder, and that's probably a bit too much digging. There's too much force going in trying to get that much material.
In addition to the width, what about the center of what's the line, what's the wheel when we're doing the boat? What's it called?
Rocker bogey.
Rocker bogey. Is that going to raise our center? Like
It will make us taller, yes.
so we're off of a higher center than to begin with. Okay.
Yes.
The only other question about rocker bogey is just to make sure it can handle center of mass not being in the center.
We'll find out.
All right.
I think
We can
they
plan
work
for that.
better
I
than
think
any
it
will.
will.
Maybe a small mock model.
Ben over here has a small mock model of a rocker bogey.
I also made this one. Just to show. This one's the one.
So to John's point, we have always kind of gone on the idea of bigger is better, more regolith is the best, and that's true. If you want to win, you got to mine the most. We need 8 kilogram to qualify for mining, which isn't a whole lot. And honestly, we had 8-inch width buckets on the sand crawler, and we'd
Yes.
probably get it up. We'd probably get 8 kilogram if we got the mechanism to work in mine with 4-inch. We don't need that much space.
I guess you're right. As long as we're autonomous, we only care if we get 1 kilo.
And like with it being wider, it's gonna take a lot more time and effort to get it in, to get to that layer where you can start doing stuff. With it narrower, you get there quicker and you just spend more time actually digging.
That's true.
So it's kind of a trade-off. I'm sure there's a
Yes.
cross point.
All right,
here.
Thayer, then we need to move on.
I just had one more question about the bucket ladder, and I'm sure this is open for discussion at a later point, but I just wanted to know, was the idea that you would do the kind of unfolding mechanism that you did on the Sandcrawler last year, or some method of having a shorter one and lowering it into the ground?
Simpler is better, but we hadn't gotten that far.
Okay.
Yep.
What is the scissoring system of last year's?
It was a Z pattern that was.
Good
had-
question. Later.
Yeah.
Okay. Did it have to do with Justin and Trent?
Yes.
Yeah.
Okay. Yeah. It's probably like the snakes then.
Tina?
That's all I need.
Alright, so these were the top 4 batteries that we were deciding on last week. After we talked last week and did the weighted matrix, we pretty much decided that NMC or INR would be best. I went to three different ones. LiPo, INR, and NMC. I actually did some calculations on how many amp hours we could get for or how many amps we could get for 10 minutes continuously, and the NMC could not handle it very well at all. So we're down to the INR or the LiPo, and if we go with the 24 volt system, then I think the INR would be best. We can use the individual cells and build our own custom whatever we want. We would need 30-ish. I don't remember how many actually. Anyway, if we want smaller space, we might have to go with the LiPos. It kind of depends on what voltage system we end up going with. We have, I don't know. Do you have any questions? Yes.
So how does the weight compare between the batteries, kind of versus how much amperage we can get out of it?
So there are a lot of different kind of LiPo batteries. They're used a lot in hobby electronics, quadcopters, scooters, tons of stuff. So you could get those in pretty much anything you want. So there are a lot of options with LiPo. With these, they each weigh about 47 grams, which, with a lot of batteries, that can add up pretty quickly.
47 grams per 3 amp hours per 3.2 volts. So there's 3 different variables you're looking at here. I think overall, is it okay if I hijack?
Yeah, go for it.
I think overall LiPo is going to be a little bit lighter because they don't have the full metal casing around them that the INRs do.
Right. Were you saying the LiPos were going to take up a little space too?
Yeah, they're a little bit you can get them in different sizes, and there are a lot that are flat, kind of like bags, and so you could just fit them in somewhere. That being said, they're not quite as protected as the cylinders. So the cylinders are a hard cell; it's harder to punch through them. Whereas the bags, if you got something sharp and jabbed it, it would definitely go through. It wouldn't be a great time.
So is 40 amps continuous discharge enough?
No.
Okay.
So
how
that
is
is
INR an option?
So
INR. So
that's
basically,
per cell.
yeah, that's
right,
per cell.
but if you're having if you're having
We would-
14 cells,
We would have
7 in
probably
series and
4 or 5 in parallel, and then for 10 minutes, for 5 in parallel, we could get 90 amps for 10 minutes continuously.
4 in parallel is going to be
5 in parallel.
5 in parallel.
Yeah. So if you had
So you
five of
would
those
need-
in parallel,
But we need
exactly
7 times that in order to get enough voltage. So 7 times 5.
It's 35 cells.
Yeah.
We had
35 cells.
24 on our last robot, and we can build these to almost any.
we had
square
more
shape.
than that, didn't we?
We had
16 per block, and then
Oh,
we had
36.
We had 36 in our last
So we'd be,
one.
we'd be losing 1 cell. And
So it's a reasonable amount, technically. Aaron.
What's the weight for that? How much?
Which
what's
one?
the weight per cell of
This
the
one?
different models? I don't see weight on there.
I should have added weight. Okay, so the INR is 47 grams per cell, so times that by 35 or so. And then the LiPo, there's a huge variety. One that I was looking at was 745 grams, but that was with I don't know, it was with a ton of amps. Yes.
So 2 things. First of all, with LiPo, couldn't you just build a hard covering around
Yeah,
it?
that's a good point. We could just do that.
Or just be careful.
Or both.
But these are mechanical
Probably
engineers.
the hard
talking
covering.
about-
No, it's okay. We won't
But,
let them play with the batteries until they're ready.
But is it possible for electrical to just get to like figure out to get however much draw and voltage they want, and basically figure out how heavy each of those two collections of batteries would be?
So however much the power we need is dependent on what the robot is. And to be honest, we're still figuring out exactly how to do that accurately, because last year we thought we needed a lot less than we actually needed. We're trying to learn from that mistake and give us a little bit of a buffer, but again, we're not sure exactly how much power we're going to use. So that's part of the reason I'm not sure which one
But
we
yes, we
go
can do a
for.
calculation of LiPo versus these cylindrical cells
Yes.
with an equal power capacity, voltage, and weight type thing.
Because it kind of sounds like the main thing is weight here versus each other.
Weight, size, and capacity.
Yeah.
Three
I mean, like,
things that.
in terms of.
I'm just kind of curious between LiPo and IR, what is the relative kind of cost of each of the systems?
That's a good question. The INR is pretty expensive per cell. It's about $6.50 per cell, so multiplied by 35 or so, that's quite a bit of money. The other one was the LiPo that we were looking at. Just one of the options was about $71. So price-wise, it sounds like the LiPo might be a little better.
LiPo's about a third as expensive.
Yeah.
And just so people know, I did the calculation for the, what was it, 5 in series times 7, or 7 times 5, whatever it was. The 36 cells of the INR, it's 1.65 kilograms.
Okay.
For weight
John.
wise.
I was gonna say with the LiPo, it seems like we could get batteries that give us a little bit more voltage and amperage per battery that are a little bit heavier.
Mhm.
And so I think the advantage there it would be easier to manage less batteries.
This is true. And if we built a case for it, I mean, that would be good too.
So for the INR batteries, is the main advantage kind of like the customizability of everything?
Yeah.
We can build them into a
The
pack
fun
that
aspect.
is any size that or any
We-
shape that we want. So we can build a pack that fits into a certain size.
Tino?
Sorry.
Is that so this would be a set, one complete set for the power for like 35 cells that'd be operating the rover for 10 minutes in the competition?
Yeah. So that 35 cells would give us like, I think I said 90 or so amps continuously. So we're not going to use 90 amps for the entire 10 minutes unless something is really weird. Because there's no way we're going to use 90 continuously for 10 minutes. But worst case scenario, we could use a max of 90 amps for 10 minutes straight. That should be enough.
Would we have to do that with a single LiPo?
Come again?
Would we be able to do that with a single LiPo battery?
We should be able to, yes. Let's see. I mean, there's enough options out there that we could find one.
If you had one LiPo battery and you just had one battery, you wouldn't even need to manage batteries. You just have one.
Well, that's not entirely true because they come in one pack, but they're like multiple batteries just pre-made for us. So, I mean, there are technically still a lot of batteries, just not. Okay.
I just have another question about the difference between the two of them, because I know that LiPos, when used, not well, have the potential to be very explosive.
You guys heard of the Robo-Utes? That was LiPos. They burned down their lab with these type of batteries.
Yeah.
So
Do the INRs have the same explosive potential?
So to be fair, all of these batteries are very dangerous. All of them have the potential to explode. Safety-wise, they all seemed relatively equal. Some claim to be a little safer than others, but they're all about the same. That is why I was concerned about the soft shell, though, because they are easier to punch through, and then they do have a tendency to overheat and start fires. So that's not fun. But
If we manage the temperature and a case around it.
if we did build a custom case, which is a really good idea. I honestly hadn't thought that far, but yes, Logan.
Do we need to make multiple spare like battery packs?
In the past, we've had a competition set and a practice set. We had two.
Well, last year
we did not trash.
Last year we made a practice set and a competition set, and then we didn't have enough power, so we put them together.
Put them both.
But
So
yes, we would probably buy one for practice, one for competition. If nothing else, it would be like a backup in case one blew up in Florida, and then we'd have another one that we could just swap in.
Alright, so it kind of looks like lipos with a cover.
That
Is the way people are
sounds
leaning.
pretty good.
So what does it mean it can't easily build custom packs?
So we would have to buy a pack that has the voltage and current that we need. We couldn't configure it, we couldn't build it to the exact specifications we need. We would have to find it online.
And if something was to change in the middle of building a robot that made us need more current or voltage?
Then we would probably have to buy another battery.
Well, you
like
can
a
combine-
different
The thing about lipos is that they are built like everywhere. They're the most
Yeah.
widely used batteries, so you're gonna be able to find the
So-
configuration
Yeah.
that you want.
Can you not combine them in parallel to get more current?
Yes, you can.
Yeah.
So, yeah, that's one thing we could do. And we'd probably have to double fuse them up to get the voltage we need anyway, wouldn't we?
No, they come in like
They come in
they come in
20
20 or 30
Okay.
or 40
To-
volt.
to do-
if we were to change power specifications. we
Well,
would
like,
just
if we had like an amperage need, we need to combine them in parallel, so they'd need to be like the same battery. So if we had like a 22, like a big pack, we would need the same voltage in parallel with that.
So I might add a plus on that is instead you can't easily build custom pack, it's you can buy it commercial off the shelf and
This
you
is
know
true.
that it's probably good.
Star Wars, so
Yeah, right. So we talked about these batteries can be explosive. Like in the case that it does explode, how much damage is that gonna maybe cause to other things?
Burn down the lab.
It can burn, it can melt things.
It's bad.
It wouldn't be great.
We would be down a robot.
Into the club. Yeah.
That being said, I believe the electrical team also wanted to design a battery management system.
So
That's the next
that's
slide.
that's another slide.
So,
But
since
we can go there in a minute.
kind of just in general, or
Just like a side note, if you're gonna build a special case that houses this thing in, is there any issue with throwing a little bit of baking soda so you have a self-contained thermal runaway kit?
No.
Baking soda doesn't quite work with lithium. It only works with lead acid.
Oh, okay.
So
I don't know
There are
what.
other kinds of returns that work.
We could probably look into that though. That's a
built in.
great
So they
idea.
also sell lipo bags.
Yeah, I was gonna say they sell the bags if we want to just put it in a bag too.
But also, in general, testing robot, carry fire extinguisher, don't leave batteries in the robot.
And do not leave them alone when charging them.
or
They
would they?
just like probably none of you guys will be charging them, or very few of you will be. That will be the responsibility of the electrical team, probably primarily myself and Cole. For the most part, we're going to recommend that everyone else leave the batteries alone. So that's one of the safety features we're going for. Most people don't touch it.
Alright, sounds like lipos with kind of built-in safety system and cover. Electrical school?
Lipos it is, guys.
Alright, 2 more slides, and then we make TED Talk again.
Oh, okay.
Software has a slide. Oh, software has a slide too. 3 more slides. Yeah.
John Robe, you're still important to us.
What?
You've got a slide in a couple slides.
Oh yeah.
Alright,
So-
next up.
For our battery protection system, we had basically 2 options that we could think of: to add on a BMS or to have a fuse or maybe multiple fuses and then just charge it with the BMS.
Can you define BMS?
A BMS is a battery management system. It makes sure that your batteries all charge at the same rate and discharge at the same rate, because that's important with batteries for several reasons that I won't get into. The problem we had with the BMS last year was it was difficult to locate one that had the capacity we needed. Like most of them that we saw cut off at like 30 amps. Again, we thought that would be enough. It was not. And so the BMS has the potential of shutting off the robot before we're ready for it to, because it thinks there's a short. But on the plus side, if there were a short, it would immediately shut off the robot. So that would solve several problems. With the fuse, that would also shut off the robot, so it is potentially just as safe. I I'm not positive about this, but I think it would be slower to shut off the robot because you have to burn through the fuse first. Go ahead,
Yes,
John.
just
Please.
like minusculely longer, but yeah.
It also allows for more transient voltage or current spikes.
Yeah, so if we have just a spike, it's better that way. It's easy to replace fuses, like really easy. They are dirt cheap, so that's really nice. They're easy to find, easy to install. Go ahead.
You allowed to replace fuses during that 10-minute portion when the competition's going on?
No, we are not.
Alright, so if it happens then, we're shit out of luck, right?
Yeah, but that's the
Okay.
same with the BMS.
If a fuse
So-
blows on Mars, you're not replacing it.
That is the same deal with the BMS though. If it shuts off in the competition, there's not much you can do.
So I mean, if we have a hard time finding a BMS that kind of meets what we need, we want it to be tolerant to current spikes and things. I mean, I say we make our own, integrate it with what we got with the computer, let it be controlled. I mean,
If
it's
someone
more
wants to
work,
take
but
on that project, I'm not sure exactly how a BMS is designed,
that probably would be
and
me taking on that project.
it would.
So were you the one that posted on Slack?
Yep.
So yeah, we can discuss this later, but the
Yes.
main purpose of the computer is to monitor the voltages and stuff, but not control the battery.
Mostly
the
so we're
like
aware.
battery controlling or like switching MOSFETs would preferably be done by a microcontroller because of safety and
Okay,
things like
sure.
that. But
mean, whether it's just
but
like a
feeding
controller
back
or
data
not,
to the computer
regardless.
would be a good thing to do, and that's somewhere.
I mean, really, the only purpose of a BMS is to shut off the batteries if something goes dead wrong. Like, if something shorts, you don't want to start a fire, shut the batteries off. Disconnect it from the robot. But, yeah. A custom-built one, we haven't done that before, could be interesting. Otherwise, I think fuses are our best bet.
Metric-wise, it's about 50-50 at RMC if you use fuses or BMS. So, it's a coin toss.
Didn't most people use a fuse? We took a poll. Like, we walked around the room to ask everyone.
I think maybe it was 2016 I talked to people about it.
Yeah, I have a spreadsheet.
Anyway,
Anywho,
does anyone have any other questions?
preferences.
On Mars, like in terms of what NASA would they probably use a BMS?
Oh, yeah.
or
Yes.
fuses? 100% yes.
Well, they would use a reactor, but
Yeah.
That's why I'm here. So, generally BMS?
Yes, use
No,
BMS.
no.
Wait, no, we want the fuse.
We don't No, so no BMS.
Is anyone?
And then do
No
it.
BMS like last year.
They have fully programmable BMS, but they're more expensive.
Like, how expensive?
Like
Knock implementation.
10,000 Canadian.
So, I mean, that might be a little bit out of our price range.
That would be the
I mean,
cost of the
I was
robot.
just thinking Google real quick.
So on the Matrix, that one might might make that a little lower, but that's good to know.
So
Thanks.
I don't know if there's cheaper ones. That was just the first Google result.
Right. Okay.
Some startup.
Yes.
Well, would it work to plan on a fuse and then if a program that is made is working well, then to use that instead?
That should work. In fact, we could probably have both. I
That's what we
mean,
did last year is we had a fuse.
we had a single fuse.
Well, and the other thing we discovered last year is that our motor controllers have low voltage cutoffs. One of the dangers with lithium batteries is if you over discharge them, and so our motor controllers can detect that and stop things from happening.
It's not like explosive dangerous. It's like you could ruin your battery dangerous.
And like when you charge it back up, they blow up.
Which we did twice. Well, we didn't blow them up, but we over discharged them twice 2 years ago. Well, I did.
Alright, so I was wrong the first time. Fuses, it looks like. Fuses.
Fuses with optional
So
add-on.
we decided to make our own BMS. Cool.
Alright.
Next slide. This one will be quick because we're running out of time. Motors. There's either brushed motors, which are motors that you think of everywhere. They have brushes in them. That's why they're called brushed. And then there's brushless motors, which don't have brushes. So brush motors, they're super easy to control. You apply voltage, they spin. There's only 2 terminals on them. They're less power efficient, so that may not be a good thing when we're looking at our current draw and how much power we're actually throwing into the ground when we're
moving everywhere. They have a negative speed torque curve, meaning that at lower speeds they have their most torque, but then as you increase speeds, their torque goes down. They're extremely easy to find at low cost and variety, so you can go to Robot Shop or anywhere basically and find a motor with a gearbox on it that you can just plug in and work. And then gearbox availability. The gearboxes for brushed motors are everywhere. They most of the time come with the motor. And then you normally have a larger range of size and power ratio to choose from.
Also cheaper.
Yeah, much cheaper. Depending on what you look at. Brushless motors are harder to control. You have to apply voltages to 3 different pins in a different sequence. But because you're doing that, they become much more efficient, anywhere from 90 to 95% efficient, which is insane. They have a flatter speed torque curve, meaning that you get a more of a consistent torque across all of your speeds, which is important if we're throwing it into a high-speed gearbox. They're harder to find in the lower power and speed range, so typically you would get a higher RPM motor, then throw it through a gearbox, which is effectively what you're doing with these brush motors as well. But the problem is that it's harder to find a gearbox for brushless motors. So one thing that I've seen is you get a drill gearbox for like a Bosch drill, tear that apart, and you have a planetary gearbox that you can attach to anything. And then, but they come in a super small package for their power. So if we're tight on space, we can just get a motor that's that big, but it's like a pancake motor that has a high power output that we need for certain applications. What we were kind of leaning towards was use brushless on the drive kind of mechanism and kind of have that be our main focus there, and then use brushed where applicable because brushless isn't going to solve all of our problems. One thing I kind of want to look at is hoverboard motors. They are super cheap, high torque, and they could work well for drive motors and such. Kind of breeze through that.
Have you found good options, I mean, other than that one?
For
like
motors?
To like buy, purchase, that we can actually do?
Yeah, so there's hoverboard motors, which you have to get off eBay, and they're kind of sketchy. They do have higher torque motors, more meant for quadcopters or RC cars, but they're in that low low kV rating, which basically means they have higher torque. So higher torque range, and then we just have to mount it to a wheel, or preferably throw it through a gearbox. I think we're gonna have to do that with any motor we choose, is throw it through a gearbox.
Have we found a good gearbox?
That it could be as simple as a simple belt and pulley gear reduction, but that's something that we haven't looked into. That's more of a mechanical thing. Yeah.
Just me personally, I think, especially in high torque applications like this, like you were saying, you really don't want to run any motor at its free speed.
Mm-hmm.
You're not gonna do a whole lot, and so I think when you have easier gearbox availability, when you have to gear down your motor and you have to, that's just a better thing to do.
Mm-hmm.
Either of these run into problems with BP1 getting, say, the gearbox or the motor itself or anything?
So
EV1s get everywhere.
Yeah, brushless motors are actually better at that since they don't have any touching parts.
Oh, there's no commutator?
Yeah, there's no commutator to actually tell which coils to fire. It's kind of a weird way of putting it. But these are much more dust resistant than brushed motors. If you get dust in there, they'll gum up and then eventually stop working.
That said, we've never had a brush motor fail due to BP1. We've broken them, but we haven't had them break because of BP1 ingress.
We've also put motor covers on them, but
yeah.
Have you guys used brushless motors in the past?
No. So that's something that's the innovative part that the electrical team's trying to lean towards.
Checked to make sure that we can get motor controllers with the correct current output for what we need to drive? O-Drive is where we're kind of leaning towards on that, and availability is, last I checked, pretty good on those. Okay.
So.
Just so it's out there, you can also buy sealed brush motors.
Yeah.
Have no holes in them.
Yeah.
And when it comes to encoders, I'm guessing that they're easier to use with brush motors, but I don't know if brushless.
Ease of use is the same between both of them. You just attach an encoder to the output, and it works.
Isn't there censored brushless as well?
They do have censored brushless motors,
the censored part of that is mostly used to operate at low speeds because of just how you have to control brushless motors. So the thing with like hoverboard motors, those have the sensors built in. The motor controllers we want to use can operate with those. If not, there are cheap $15 encoders that we can throw on there that act as the sensors in a censored brushless motor. Yeah.
Why would we go with a hybrid approach of some brushless, some brushless, as opposed to all brushless?
Because sometimes we're just in a pinch to get a motor that we know works, that has a gearbox on it, and that the controllers are cheap and easy to use. So I'm thinking for a digging mechanism, anything on the upper half of the robot that we just need to know works and just get it out of the way. Use a brush motor on that. But for the drive, it's a little bit more applicable because that's closer to the ground, closer to the dust, and smaller package for the brushless. So that's why I'm kind of going for, so we're not diving headfirst into the shallow end of the pool. So
Fair.
I was also just wondering, are there published like torque curves and things on most of these brushless motors, or like if we bought them, would we not have that information?
It depends. Most of the time, they're all coming out of China, so unless somebody has done independent research on it, you're likely not to get a torque curve out of it.
It all depends on the gearbox.
Yeah, because like they're easier to find with brush motors. You know, people
Yeah, well,
done those
if you look at like your sample size, brushed motors is 100 and brushless maybe 10.
Yeah.
So
no,
your sample size
I get
is
that. I'm just saying, it's when you have that information, it makes it easier to design with a brush motor than a brushless motor.
Yes.
Does anyone have any huge complaints of having this hybrid between the two?
I think we're going to need something smaller for a rocker bogie system. So I think we kind of have to go with the brushless if we're doing rocker bogie.
I agree.
Yeah.
For the rocker bogie as well, for the train, would we still have brushless motors? Or would we
For turning, like
The actuator, yeah.
The actuator? Sure. We'd probably have to throw those through a massive gearbox. So that would be a mechanical, electrical crossover episode where we episode like coming next Thursday.
There we go.
At 7 o'clock. Yeah, so that's where we're gonna have to talk and see what we can interface, and it'll probably involve a lot of 3D printing to get the interface right. And we can do high strength nylon prints that will work well for that.
I'm not entirely sure, but couldn't you use for those actuator motors you're talking about, instead of using a big gearbox, some sort of high torque servo? Because I know there's like plenty of
High torque servos
like,
are DC motors with gearboxes.
Oh, they have gear. Okay.
Yeah.
But I mean, that'd be a good commercial off-the-shelf option if we can get ones that are accurate and strong enough.
Yes. That's the hard part is accurate and strong.
And driving servos, the servo controllers are usually not for high torque applications in terms of off-the-shelf motor controllers or servos.
Depending on what your definition of servo is, but we can get into that later.
Yeah.
So.
Sounds like we're good on motors. Any other comments? Moving on? Moving on.
Ladies and gentlemen, John Rose.
All right, so I guess in terms of programming and sensors, programming had a kind of a different animal a little bit, and just in the sense that basically we can choose any of these and not, well, what am I trying to say? We can basically pick whatever we want out of this and try to throw it on the robot some way or another. So we weren't really limiting ourselves in terms of the rest of the robot design for our selections, but we basically came up with all of these sensor systems that should be on the robot. So in terms of LiDAR was the biggest question mark in terms of how are we going to use it effectively. So how many of you here know what LiDAR is? Okay. Some people don't have their hands up. Basically, it's a laser that shoots out, and you have a sensor that spins something in a circle, and it's a spinning laser that's basically bouncing off of things and measuring the distance to and from them.
Roombas,
Huh?
Roombas?
I don't think Roombas.
I think like the $900 Roombas.
But LiDAR
in our competition, it's really actually difficult to mount the LiDAR in a useful place on a robot. And especially if we're going with a belt digger system, it's going to be that much more difficult because the front of our robot will always be obscured to the LiDAR, which is basically what we want to have it scanning. Is we want to be able to have the LiDAR laser scanning basically just the obstacles and the rocks that we might be running over, so we can know to avoid them. So that's the purpose of the LiDAR. So basically, if we go and we decide that we actually want to try to integrate a LiDAR onto our robot, the biggest challenge I think might not be programming. I think it might be mechanical on how to figure out where to put a LiDAR on the robot. So how's everyone feeling about trying to get a LiDAR somewhere useful?
How big would a LiDAR be?
That.
Okay.
What are we talking
That.
weight-wise for the LiDAR?
Half a kilo max, hard max. Yeah, hard max. Probably 200, 300 grams.
Okay.
Is it something where we could get the same functionality out of something else?
Yes, which is point number 2, the stereoscopic camera. The stereoscopic camera is basically just any type of a specialized type of 3D camera, where we basically take 2 video feeds in a configuration that's like your eyeballs, and you run calculations on it to get a 3D point cloud of everything that's in front of you on the robot. So in terms of our design and programming and what we talked about yesterday, we're 100% going to have a stereoscopic camera on the robot, because basically in terms of robustness and usability, stereoscopic camera is going to be our best bet for detecting obstacles. Go ahead.
Is there a point to LiDAR then?
So yes, because the stereoscopic camera, especially when you're in a gray pit full of a bunch of gray dust that's getting kicked up everywhere, the cameras that we're using can get blurry and get confused about the differences between the two, because there aren't very many defining features in the arena that we're supposed to use.
Gotcha.
I mean, obviously the stereoscopic cameras will see the walls really well, but we can't use that for localization and that kind of thing. So, yeah.
Would there be any benefit to having multiple stereoscopic camera systems on the robot?
Potentially. It's not something that I've thought about too much, but if we have one in the front and one in the back, then we could probably use it for point number 4 for the localization and trying to figure out where we are in the arena. Yeah.
Well, and as far as error rate, could you get kind of 2 different point clouds and try and analyze them together to kind of reduce that error?
Yeah, I don't know how much it'll actually help though.
I mean, it wouldn't take anything.
Yeah, yeah. That.
If LiDAR's having problems seeing the front, how far out will the LiDAR see? Could we like do some dead rendering stuff to like infer our location based off of previous scan locations to know what will
If it's
be in front of us, even if we're occluded directly in front of us at the time?
So if we're occluded by our digger, you mean?
Yeah. Because
Yeah.
if we mount that high up, we could see like at least 10 feet out, and when we're 10 feet back, we can infer where we're at now.
Yep. Yeah, and that's definitely useful, because we'll have the IMU in order to actually detect when we've moved 10 feet forward, and the wheel odometry. So we once we get to that point, we can say, oh, there's probably an obstacle here, and we'd have that in our 3D map already. It's not as good as having the real-time data though, because in terms of the kind of error detection and algorithms to reduce the error from like the stereoscopic cameras, older data gets lower priority in terms of overriding things. So if the stereoscopic camera will later see that there's no obstacle there, it's just like if I was walking in front of the robot and I walked away, then it'll remove me as an obstacle, because if the robot's stationary, you know. So it's a little tricky, and we'd have to configure it very specifically to make that very useful.
John, I have a question.
Yeah.
So I worked with the Z stereo camera a little bit last year, and my experience with it is that like it has a lower limit on the distance at which it can generate a point cloud. So like, it will only really register things that are maybe like 3 feet in front of it.
Yep.
Is that pretty common for stereoscopic cameras?
Yeah.
Okay.
Yeah, it's real common. Also, you may not have noticed, but there's a configuration in the ROS launch file to ignore anything close.
Oh.
So that might have been on it. Yeah.
Don't you have the same positioning like issue with the stereoscopic camera?
Yes, but the stereoscopic camera has a 3D field of view, right? So the stereoscopic camera can see up and down. The laser is just a 2D plane.
Okay.
So that's why it's a lot easier to mount it, because you can mount it level and higher up, and it will obviously be able to see down lower. But if you mount a laser higher up and it's scanning horizontally and not angled, then you're only going to be detecting the walls.
Could you mount a laser higher up and have it kind of like angled down in front of it? Okay.
So we tried that 3 years ago. Master Chief.
That was with a actuator.
Yeah, and we were gonna have an actuator. The calculations for that are gonna be massively difficult, but we can try that again.
They got a lot of cool jokes.
It was cool.
Can't we just let the digger be in its back instead of front, so while it's moving, it's reading clearly, but when it's there.
That's clever.
That's actually extremely clever. I never even thought about that. So I mean, maybe you define your back or your front as where you're driving. That's actually incredibly smart. I have never even thought about that. Yeah.
It's a good idea, but then I mean, it's not a huge problem, but you have to turn around every time you come back.
No, not necessarily.
When you come back.
Or just work under the assumption that you're
So, not necessarily. So,
that you can follow the same path backwards that you did forwards.
So I actually like this idea so much because you can start in there. Where's my marker? So let's say this is a competition area, right? So the digging area starts here. So instead we have our robot drive out further to here, so that the front of the robot will be closer to the edge, but our digger can actually dig right here still. And so we only need to go front and back and front and back and front and back. Does that make sense? So
Yeah,
we drive just a little bit further.
As long as you can follow the same path back to the collector bin
And that is
without the camera.
And that assumes that you're not running
Because you have to turn around and use
So,
the camera.
You're right.
Other thing to point out, like I said in the beginning, NASA will put you in a random position and orientation, so you're not guaranteed to know which way your robot's going to be pointing.
We'll get to that in a second.
Start the localization.
Yeah. Yeah.
I just thought of this, like, what kind of way to, like, I think I saw one thing where it had a laser kind of thing that projects like a grid or something. Would that be able to help, like, the stereoscopic camera recognize features better?
So there are like 3D laser or LiDAR systems. Those are a lot more expensive and we've never used them before. But they are a lot more useful because you'll actually get that plane. So that's something that if we are going to use a LiDAR, I think we'd have to use one that has a 3D component. Go ahead.
I was just going to say, a lot of the 3D LiDARs that are out there are around the $4,000 range, and they're built for like really long distance, area detection, which doesn't sound like would really be necessary for the competition.
I saw a couple. I don't know the price though. That's the trick. So we'd have to get it sponsored. Yeah, go ahead.
Okay, so I was just gonna say, could we put the LiDAR on the back of the robot so we could follow that straight path back, and it would just scan for bigger obstacles? Because if we're just driving backwards, robot's a little bit off the ground anyways. That's all we really care about.
Yep. Yeah. And the trick is if your back is now the thing with the digger, then you're gonna have to figure that out on where to put the LiDAR again.
You have to turn around and just follow the dead reckoning.
Yeah. Or you could put your LiDAR out over the rocker bogie wheels on a plane above it. That's actually something that might be nice. Yeah.
Have you seen any other teams do that?
Alabama had a LiDAR. Well, every year Alabama has used a LiDAR low to the ground as their autonomy system.
And they kind of had it like offset from the center of the robot, so the digger wasn't in the way of it, right?
Well, yeah, maybe last year. 2 years ago, it was in the center of the back.
Oh.
But But if you have a platform over the wheels, over the rocker bogie wheels, that you put the LiDAR on, that might work really well.
So what we could do is just say, let's use a
Depends on
LiDAR
what
and
we
make
do.
a requirement for mechanical to make sure the digging mechanism doesn't obstruct the LiDAR. Does that sound good?
That works.
Okay.
Cool.
We're higher because of this rocker bogey. Maybe the lighter on here
It could be like
Yeah,
stuff under some
If it's even like that high above the ground, it's totally fine. Especially if we're using a 3D LiDAR system. If we're not, then we kind of have to tilt it a little bit. But as long as we're not really the 0.75 meters off the ground like we were previously, then I think we're good. Any other hands? Okay, so I think that's enough of the LiDAR. Stereoscopic camera, we're definitely going to use. Mechanical's going to have to figure out where it's going to go. Yeah.
Use the LiDAR on your back and then have your stereoscopic camera on the other side so that when you're backing up, you're not totally blind.
Yeah, and I think he mentioned that. But
Okay,
yeah,
alright.
that's a really good idea. So in terms of IMU, we're going to use the Northrop Grumman one that we have. We're going to have a backup one, though, put on the robot in the electrical container as well. I mean, there's not really any other option for these kind of sensor systems, so that's why we're not having a this one versus this one kind of discussion with these. It's mostly just we are using this because there's, in terms of sensor systems, there aren't really many other cool sensor systems that I know of that will do these kind of detections. So we're going to have a backup IMU. Collector bin localization system, however, is something that I wanted to really get opinions on. We're kind of struggling trying to come up with the best option for this. So sorry I don't have a comparison slide, but basically there are two options right now that we're looking into pursuing. One is having a radar type sensor tag system, so you'd have a radar transmitter or receiver on the collector bin, and then that would basically send out radar pings, shortwave radar pings to the robot, and you'd use those pings to detect your location.
You could use two on each side of the collector.
Yes, we definitely have two, and then you'd use it to triangulate. So that's the system that I've never. I don't know where we get those sensors. I don't know how to get the transmitters. I've never seen it before, so as much help as I can get on that, that'd be great. Yeah.
Would the walls confuse that at all? Like, would it bounce
It
off the walls
shouldn't for
maybe?
radar.
They're wood walls, right?
I don't know.
They're, some of them are, well, it's a steel container you're competing with.
Yeah, it's a steel
Oh,
container. The
the
collector bins
box.
would, but you'd have a direct line of sight, effectively to the. I mean, you're going to get echoes, but
Okay.
I think it'd be okay. Yeah.
Just a point of clarification for me. The collector bin is on the side of the pit, is here, correct?
Yes,
Yeah.
it
Not
is
in the back.
inside the pit.
Yeah.
It's on the side, on the inside.
So that's actually why other localization systems are kind of a lot more difficult now. So Aruco tags or tags for our camera to look at and see this is where the collector bin is, and I've got a 3D point to that, aren't really going to be as feasible now because those tags would have to be placed perpendicular to where you're driving. So you're not going to be able to see those when you're driving the opposite way. Yeah.
You have a,
I know you have a LED.
no, like one on each corner.
Can you put it on the short side?
That's a good question.
That's what I want to know.
Okay,
Yeah.
But-
Because if you can't put it on the short side, then that's a real
Okay,
big
yeah.
problem. If you can, then that's a little different. But we're gonna have to check the rules on that. Yeah.
Isn't the Aruco marker just to locate the bin though, not to tell how far away you are from it?
No, with
do
a
both.
3D camera, it'll actually tell you how far.
Or
Well,
even a
but
2D
that's-
camera.
It doesn't have to because we're gonna have the LiDAR and the stereoscopic.
Well, a stereoscopic camera is what does
Right.
it. But yeah.
But like, what if you just had it there and then your robot located it, marked it in its map or whatever, and then went off and did its thing and just knew where it was?
That's usually what it is. That's usually what you do. The problem is, if we don't have the IMU calibrated well, then we're not going to have a really good sensor data for how we've actually moved. I think we're going to be able to get the IMU calibrated well. We're just going to have to figure that out. The other thing is the wheel slippage. So your odometry will never be accurate enough to make that perfect. But but it's something that you can use to a certain degree of accuracy before you kind of have to start not trusting it. Go ahead.
Right, but I mean, we have a pretty accurate IMU. This is like the one that NASA uses. And if we're using, the 6-wheel system, they all spin independently, we have enough odometry data to try and correct that reasonably well, at least.
Yeah, we should.
Excellent.
And I mean, this is just something that we're just gonna have to work on. And as long as we've got a long enough time for programming to kind of configure this and test it and get it all calibrated, then I think we can get the localization done really well.
Do you think it would be worth it to kind of like have a few different options and prototype multiple things to see which works best?
For localization system?
Yeah.
Yeah. I think we're gonna be pursuing, well, if we can get if we can figure out a purchase list for the radio markers, I think that's option number one, because that sounds the best.
Except like, we don't have any idea of like any commercial off-the-shelf options for
Correct.
radio beacons.
Yeah.
Okay.
Yeah, go ahead.
Yeah, so I found some passive RF tags and beacons on Amazon for $50.
Sweet. That perfect.
Well, and I mean, if that doesn't work, you can use the camera and another good tag, or
Yep.
retro
We're
reflective
probably
tag.
going to be using multiple options as having them in there as a backup,
So
in case one of them doesn't work.
Let's try to pick 2 to prototype and have those in mind to present next week.
Sound like LiDAR sounding pretty epic.
We're
gonna
doing a
do
LiDAR, we're doing a stereoscopic camera.
We're trying to figure out localization.
We're doing a backup IMU. Localization system. The third option is having HTC Vive lighthouses broadcasting, and then sensor tags on the robot to get the lighthouse beacon data and calibrate our position using that. Those are going to also be a lot more difficult because of the collector bin being perpendicular to driving, because it won't give you really good data on your distance in one of the axes, because the lighthouses won't be perpendicular, parallel, whatever. Your lighthouses are in a plane, but yeah.
Pause real quick. So it is close to 7:30. We've got the rest of John's stuff and Ted has a short presentation. If you have to go at 7:30, by all means, we'll be sending out the presentation later. But we might run a little bit over than I said we would. So if you could stay, that'd be awesome. Might be going a little bit late, but if you have to go, we won't keep it.
Were there any other ideas on localization systems?
I mean, it's not something you really don't have already, but my suggestion would be, if you were going to go with tags on like Aruco tags, I would go with, I put it in the Google Doc somewhere, about just retro-reflective panels and green light, just because it's a lot easier to see.
Yeah. We were actually having pretty big issues with that when we tried to do it previously. It should have seen it, but it wasn't. So yeah, getting the correct tag is actually really important. So it's good. Okay, if that's everything, I think we're gonna bin that for now, and we'll come back to it next week. Odometry depends on the motors. Really, the $12 ones that Cole mentioned earlier is probably all that we need for the motor odometry. For any linear actuators, hopefully that's built into the motors the actuators that we're using. So lastly, computing. We've got, basically, we're going to use the TX2 from last year. That's pretty well decided. There are 2 more options that we're still looking into in terms of the Intel NUC. They have a new one with a graphics card that might actually work for us. And the new NVIDIA one won't be out in time, or else we would be looking into that. But okay. Lastly, motor controllers, something that we're gonna just have to collab with electrical. But yeah. So we've got a few options, and basically we're looking at the same things that we used last year, which are Pololu, basic motor controllers, the RoboClaw, and if we're doing brushless motors, we're gonna have to look into the O-Drive. Yeah. Okay, so that's all I got.
Thank you, John, and thank you, my team leads. Okay, so we basically just did that. So I want to have a short discussion. Think for a second, like, you got an idea of what this robot's going to look like. Think of what's going to go wrong, other than we may not know how to build a rocker bogie, and our batteries might catch on fire. We've already kind of touched those. And just raise your hand whenever you think of it.
Autonomy might never localize.
Be optimistic as you're thinking of these things.
An example being, we might break a chain.
If we do a chain for the belt digger.
Do a chain for the belt digger.
Okay. I'm writing these down as we go. Yeah.
So if we go for the going forward and backwards idea, the rocker bogey doesn't work very well going backwards, does it?
I think it should do well any direction, right?
I think that's right, actually. A rocker bogey model dude just left.
But there?
I do think they don't work as well backwards, but also when you're building on a moving chassis, that's a lot harder than, it's difficult to build on a wheelbase that moves up and down.
Okay, so problems with building on articulating wheelbase.
And going with that load balance, it's easy to drive something that doesn't have a load on it around, but when you've got a couple kilos of regolith in there,
So we'll try to address that in our prototyping phase, but yeah.
Put some weights on there.
Oh, there it is.
So rocker balance problems. Any other things that could go terribly wrong and crash the mission?
The rocker bogey and the belt, the bucket belt, I'm gonna feel like your weight's gonna be more than we was last year.
Second.
Because you're doing a rocker bogey run, it goes to 3 less your weight.
So you have the extra weight of the motors, which might be accommodated for by brushless motors, and then you have 2 extra wheels.
Yeah.
So the wheels this year will probably be about 1 kilogram a pop, which is pretty light. So 6 kilograms for wheels. I can't, since I don't know about brushless motors, I can't get weight off that. It will be more than the Sandcrawler's done before, but it will be something less than what Master Chief or Amy has for treads. The bucket will be about the same.
Treads are extremely heavy.
There?
You could torch a motor anywhere.
Okay. Motor death.
If they're brushless, is that less likely?
What's the motor failure on a brushless? I'd say
Oh,
they're
yeah, less likely. Yeah, yeah.
because they have no commutators or any mechanical complexity really.
Yeah.
So I'd say they're a bit more likely.
Trash your gearbox.
But if we dump like an absurd amount of current on it, then it will die.
There is no motor that will take that. I think, I think the gearbox would fail before the gearbox would 100% fail before any brushless motor would.
Which is kind of a bonus because then we can just replace a gearbox instead of replacing the whole motor. But yes.
Any sort of event that would blind or otherwise mess up any of our sensors through localization?
So, fortunately, this competition's indoors this year, which is great. Past years, we've had, if you ever relied on anything with infrared, sunlight is a huge problem.
I know.
So.
Humidity also affected the vision.
Oh, fog.
Yep.
So we just yell at NASA, there's no humidity on Mars.
It's great. You'll see these NASA PhD engineers, and they spend their entire day in this hot room cleaning off windows for you. So you can
Oh
see
yeah,
it
like
so
they'll have a
good.
squeegee. Which that's the other thing will be in an air-conditioned building, and I believe air conditioners also reduce the humidity in a space.
In Florida, they definitely
Okay.
do.
So that's worth noting. They get the pits ready, so it's gonna be different this year, but they get the pits ready about 2 or 3 months in advance of dehumidifying this regolith. Last year, that was a problem of they only dehumidify for about a month instead of the normal 3. So we'll see what we do this year. It will depend, but that is a factor we'll have to take into account with mobility, is how wet the regolith will be. Hopefully not very.
Just tell them to let us borrow the regolith for a month, and then all the
they'll
water
do it.
will seep out. Okay, so any other major concerns before I move on? Sweet.
That dance was kind of concerning.
Don't worry about it, Dave. Okay, I'm going to talk briefly about Phase B. I kind of mentioned it before. but we are going to, do the preliminary design and prototyping, and hopefully we're going to try and knock out some of some bigger design goals, and so that we can kind of shorten the time that we're in our detailed design phase. So now I'm just going to give you a quick schedule for Phase B. We're kind of extending it to a bit over a month. So, yeah, we already talked about that. So, sorry about the gray font. I should have thought of that. So starting in next week's meeting, we're going to try and go into some further details about prototype goals, and we're actually going to start breaking out into teams and beginning design. And so something that's probably going to be different from what we've been doing up to this point is your team leads are probably going to try and schedule another time to meet during the week so that you can get some more work done on your individual projects for the robot.
Historically, it's usually been on the weekend.
Yeah, and I'm gonna leave it up to them to figure that out. And so after that, once we kind of got a little bit more detail on our design, me and my systems team, we're going to have a meeting where we define our interfaces. So that even though electrical may be working on one thing, mechanical's working on a different thing, both teams will know how the parts will go together. Mechanical will know where the LiDAR is supposed to go and where other sensors are supposed to live, so that when we all meet up at the end of the day with our different parts, they'll actually fit together and work. Hopefully. That's how it's supposed to work.
You guys are so great. So amazing.
Which means, like, if you give me a design and give the rest of the team a design, commit to it. So we're not looking at a rocker bogey 1 week and then a month later come back and see that you designed a hovercraft. So.
You found me out, Ted.
It's an extreme example, but stuff like that can happen. So make sure you're communicating with the systems team and also your team leads about any design changes that you
If you
make.
do, we'll take the hovercraft.
Why didn't you consider that?
Because there's not enough air on Mars.
The Martian says there is.
Basically, for most questions you have in this team about why not this, the answer is Mars. So, and then by week 3, I want our mechanical to have a rough CAD model ready. Is that possible, Nathan?
Rough CAD model means blocks and circles.
Yeah, I believe that's like spring break, isn't it?
Fall break?
Fall break, sorry.
I wish it was spring break.
The break. So yeah, that's possible.
Okay, sounds good. And then the week after that, we'll try to kind of like begin bridging the gap between designing the thing and building the things. And so we'll try to complete any necessary design changes and then begin construction, and hopefully we'll have a new lab by then. And then the rest of it, we're gonna kind of, sorry Tina, do you have a question?
Is this the prototype chassis, or is this like the actual?
This is the
robot?
prototype.
Okay.
This is our prototyping schedule.
Okay.
Crap, I forgot what I was gonna say.
Oh, sorry.
It's okay.
Integration, or no, build and test.
Yeah, we're gonna build it and we're gonna test the stuff that we build.
So materials wise, how is the prototype going to be different than the real thing?
That is an excellent point, and I was kind of thinking that like if we get our prototype good enough, hopefully we can use a lot of parts from the prototype for the final build.
And if we're going to be building a prototype, aren't we going to have to purchase most of the stuff anyway?
Yep.
Okay.
But like I'm thinking about like raw materials, we can use cheaper stuff, like maybe wood instead of aluminum for a prototype, or other stuff like that. But yeah, for like the core expensive components, motors, controllers, sensors, yeah, a lot of the stuff we use on the prototype will probably end up being thrown into the final product.
Around?
I found a catastrophic failure.
We've never had a prototype historically.
Can you repeat that a little bit louder?
Not true.
Oh, my bad.
That thing I spray painted and brought to the Utah Mining Association.
Totally forgot about that.
Was our inaugural prototype.
Yes.
I totally forgot.
It was so bad we didn't bother taking it out of my car.
We're moving leaps and strides in this club. And also, we have the master of 3D printing, Dave Purcell, So hopefully that'll help us accelerate our prototyping a bit.
With rapid prototyping.
Yes, exactly. And as we come with prototype designs, like try to focus like on the minimum viable product to test the things that we really need to test. So we're not spending design and construction time on things that we're pretty sure are gonna work.
An entire month and a half of this to get the build design down.
Yeah, exactly. And then at the end of it, so right now I'm conducting the conceptual design review with you all. At the end of phase B, I will conduct the preliminary design review. And that's when we will make the decision whether or not we're ready to go on to phase C to build the thing. Is that the end of my slides? It sure is. So last but not least, I'm gonna check the team leads real fast. So programming, are you ready to move to phase B?
Yes.
Okay, electrical, are you ready to move to phase B?
Yeah!
Mechanical, are you ready to move to phase B?
Yes.
Mr. President, are you ready to move to phase B?
Yes.
Okay, we're now in phase B, everyone. Okay. Go home. Oh, Dave, did you have anything else? Sorry.
If you're not on Slack, come find me.
I got one
We need
little
to meet with our
announcement.
Hold up.
teams.
Aaron's got something. Aaron's got something.
I need volunteers the last weekend of fall break.
Stacy, have a car.
The Utah Mineral Collectors of Utah are doing a giant trolley drop there. They're allowing us to have our robot there to potentially drum up some more sponsors and etc. and draw some attention. So anybody willing to
What day is that?
Can you post that in the Outreach Events
13th and
channel?
14th, I will post. Yeah, I need to maybe talk to you guys before I even announce it. But yeah, be the last weekend of fall break, so a couple weeks.
So Outreach Events. Yay, get us more money.
And BT Dubs, Dave's in charge of outreach events, so if you know a group of kids that want to see a robot, talk to him.
Also, please get on Slack if you're not on it already, and especially join the channel that you're